Hey there, and welcome. Today, we're diving into the hidden rules that secretly connect everything from secret codes to the structure of crystals. We're going to uncover one of the most powerful and honestly beautiful ideas in all of math, the group.
So let me start with a question for you. What could a simple clock, a perfectly structured crystal, and a complex digital code possibly have in common? I know, it sounds like a weird riddle, right? But believe it or not, the answer is a single mathematical idea that ties them all together.
To find that link, we have to go looking for structure. You see, a huge part of math isn't just about numbers and equations, it's about finding the underlying patterns, the deep-down rules that the universe seems to play by.
Yeah, it's really all about finding a hidden set of rules. Imagine you're creating a tiny, self-contained universe. You just have a few members in it and a couple of simple, unbreakable laws. The magic happens when you see just how much order and elegance can come from something so simple.
And here's the wild part. To build this incredibly profound concept, we only need two basic ingredients. That's it, just two simple things to get started.
Okay, ingredient number one, a set. This is just a collection of things. It could be numbers, sure, but it could also be symbols or even actions like rotate 90 degrees. Let's just think of our set as the official members of a very exclusive club.
And ingredient number two is what we call a binary operation. That's just a fancy way of saying we need a single rule for combining any two members of our club. You can think of it like the club's official secret handshake. Two members get together, do the handshake, and you get a result. All right, so we've got our members and our handshake. Now we're ready for the main event. See, not just any club gets to be a group in the mathematical sense. Oh no, it has to follow four very strict, non-negotiable rules. These are the laws that make a group so powerful.
And here they are, the big four: closure, associativity, identity, and inverse. Think of these as the constitution for our club. They guarantee that the whole structure is stable, predictable, and complete. So let's break down what each of these actually means.
First up, closure. This one's super simple. It just means that when any two members perform the official handshake, the result has to also be a member of the club. You can't combine two members and suddenly get an outsider. Basically, what happens in the group stays in the group.
Second, we have associativity. This means if you have three members combining, it doesn't matter how you group them. You could have the first two do the handshake and then bring in the third, or you could have the second and third go first. Either way, the final result is exactly the same.
Third, every group needs an identity element. This is one special, unique member that's totally neutral. When any other member combines with the identity, it's left completely unchanged. It's kind of like adding 0 to a number or multiplying a number by 1. It doesn't change a thing. And last but not least, the inverse. This rule says that for every single member in the club, there's another member, its inverse, that acts like a perfect undo button. When you combine a member with its inverse, you go right back to that neutral identity element. Basically, everything you do can be undone. Okay, that's a lot of abstract rules, I know, so let's make this real. We're going to roll up our sleeves and put an actual set of numbers to the test to see if it qualifies for our exclusive club. So let's meet our candidates. Our set is going to be these four numbers: 1, -1, I, and -I. Don't worry too much about I, just think of it as a number where I times I equals -1. And our club's handshake? That's just going to be regular old multiplication. So, the big question is, does this little club follow all the rules? To figure this out, we're going to use this multiplication table. It's just a simple grid that shows us what happens when we combine any two of our members. This thing is basically our cheat sheet. Okay, let's check the rules. First up, closure. Just take a look at everything inside the grid. Do you see any numbers other than 1, -1, I, or -I? Nope. No outsiders allowed. Our set is closed. Rule 1, check. All right, how about that identity element? Check out the row and the column for the number 1. Notice how when you multiply any of our members by 1, you just get that same member right back? That means 1 is our neutral identity element. Rule 3, check. And the inverse? Remember, we're looking for pairs that get us back to our identity, which is 1. Well, if you look, I times -I equals 1. So they're inverses of each other. And what about -1? Well, -1 times -1 is also 1, so it's its own inverse. Every member has an undo button. Rule 4, check. And since we know number multiplication is always associative, Rule 2 is covered. So we did it. This set is officially a group.
So there you have it. It's official. Our set is a group. But it turns out there's one more optional rule we can look at. It's not required for membership, but groups that follow it are just a little bit nicer, a little more orderly.
And that rule is commutativity. This just means that the order you combine two members doesn't matter. So A times B is the same as B times A. Now this should feel pretty familiar, right? It's how basic addition and multiplication work. But you can't take it for granted. Not all groups have this property.
So this really lays it all out. A group that also follows this fifth rule is called an abelian group. It's just a special name for a group with that extra layer of predictable structure. In our example, it is an abelian group because I times -1 is the same as -1 times I.
Okay, so why does any of this matter? I mean, who cares about these abstract rules and imaginary number clubs? Well, it matters because once you prove that something is a group, you instantly know a ton about how it behaves without having to check every little detail.
The thing is, this simple structure, these 4 little rules, they show up everywhere. In particle physics, in how we study crystals, in computer science, in cryptography. It's the language scientists use to describe the universe at a fundamental level. And it's the foundation for keeping all our digital information safe. It's like a simple key that unlocks these incredibly complex systems.
And that kind of leaves us with one big question, doesn't it? If a system this powerful can be built from just 4 simple rules, it really makes you wonder, what other simple, hidden rules might be quietly shaping the complex world all around us?